In this video, I want to take a look at working with what's called the one-way analysis for proportions, a one-way study. And this is categorical and data analysis still, so we still have a single qualitative variable, but it's going to have k levels. So there's not just two outcomes. Somewhere in your past you probably looked at a binomial distribution where you have two outcomes. We call them success and failure. Here there's going to be several, k. Usually it's more than two. So we're not working with a binomial. We'd be working with something called a multinomial. The k levels can be any number at all. Usually, like I said, more than two. The data that we're going to collect represent counts in the various levels of the qualitative variable. And our goal is to compare what we're observing, the counts that we're seeing in our sample, to the expected counts that we're expecting because of the null hypothesis. And the null hypothesis is going to specify values for the proportions in the various categories. We'll talk more about that in a second. This is called a one-way study. And so we're trying to see if the observed counts that we're seeing in our sample match up to some preconceived notion of what the probabilities in the different levels are. All right, so let's just jump in and take a look. So the one-way study, the way that the sample is collected, the sampling design, if you will, looks like this. There are k levels. You're going to have k different outcomes that are possible. And then you have counts in the various outcomes, and those are called your sample sizes. Ni is the observed count, so N1 is the number that we see in level 1, number 2, number 3, 4, 5, all the way up through K. The total sample size, you'd sum up those N's, the Ni's, and you get your total. And then based upon the proportion that we see, and actually we do it in terms of the expected counts, that's the way the formula works, do they match? Are our preconceived proportions correct or are they incorrect? And so the way that we set this up, I'll show you on the next slide here, our null hypothesis looks like this. The k cell probabilities are P1, P2, P3 up through Pk. Now remember, P's are proportions, and so the proportions have to sum to 1. So the proportion of the outcomes in outcome 1, the proportion of the results in outcome 2, the proportion of the results in outcome 3, all the way up through K, those proportions, those probabilities have to sum to 1. And then the alternative is going to say at least two proportions differ from their specified values. And it has to be 2. If you think about it here, if these probabilities sum to 1, can only one of them be different? Nah, it doesn't work, because say the probabilities, just to give you, it's really easy math here. Say there's 4 different outcomes, 4 different levels, k is 4, and the probabilities are 0.1, 0.2, 0.3, and 0.4. Okay, 0.1, 0.2, 0.3, and 0.4. That's P1 through P4. They obviously sum to 1. 0.12, 0.2, 0.3, and 0.4 sum together to get 1. You can't have just one of those. That's wrong. Maybe P4 is really 0.5. Well, if that's the case, then at least one of the other ones has got to be smaller. Because of the constraint that the probabilities sum to 1, you can't just have one proportion being different. That's why we're going to write it the way we do. At least 2 cell probabilities differ from their specified values. Now, when we do the null and the alternative, what you've seen me do before is try to make this look like things we've seen before. In this case, we've seen a one-way study, right? We had a null hypothesis. Let's see if I can write this here and make it look pretty good. We had a null hypothesis before. Oops, let's make those colons. And we're going to say mu1 is equal to mu2 is equal to mu3 is equal to, and I'll just do 3 here. That's a terrible 3. Mu1, mu2, mu3 are all equal. The null hypothesis in the one-way study said the means were all equal, and there's a similar null hypothesis here for the one-way study. There's going to be one example where we're going to say the proportions are all the same. So if I have 4 proportions, let's say, 4 different levels, and I'm interested in doing a test like this, we'd say P1, P2, P3, and P4 are all equal. In fact, if they're all equal and they have to sum to 1, and there's 4 of them, we would know that the probabilities are all 25% or 0.25. And the alternative is going to say, at least 2 of those are different. One may be higher, one might be lower, but at least 2 of them are off. So that's one way that this test will be done, and I'm going to do an example that looks like that. However, because of the constraint right here, we can also specify the proportions to be other values. Like P1 is equal to 0.1, P2 is equal to 0.2, P3 is equal to 0.7, for instance, if there was only 3 levels. And so I can specify the proportions so that they're equal to one another, and that's going to look a lot like what we've done before, but we have a little bit more flexibility with the one-way study, and we can specify the proportions to be individual values that are different from one another so long as they sum to 1. And the test works the same way regardless. It's going to work the same. Now the test statistic, the number part, it looks kind of ugly here. Let me show you the formula. The NI is the number that you observed in your sample. The E of NI, I think I got it down here. Yeah, I do. It's the expected count in level I. So let's say we have 3 probabilities, and let me just put some probabilities up here. 0.1, the numbers I use, maybe P2 is 0.2, and P3 is 0.7. You can see that's maybe the null hypothesis, specifies the proportions this way. They sum to 1. If I sampled 100 observations, I'd expect 10 of them. I expect 10%, or 10% of the 100 is 10. I'd expect 20 in the second level. I'd expect 70 in the third level. And so expected counts would be 10 and 20 and 70 if those were the values that were specified in the null hypothesis for the proportion. Now, if I go to my sample and I don't see 10 and 20 and 70, I'm not going to be completely surprised because I never expect my null hypothesis to hit right on the money. If I saw, for instance, instead of 10, 20, and 70, if I saw 9 and 21 and 70, it'd be like, big deal. If I saw 9 and 19 and 72, I'd say, big deal. But if I saw kind of the opposite, and I saw 80 and 10 and 10, I'd be like, whoa, wait a second, that null hypothesis looks like it's way off. And so this test is going to give us a way to look at it from a probabilistic point of view to say when our sample information appears to contradict the null hypothesis. Okay, so that's the way the test statistic is going to be put together. Again, as we've seen with all the test statistics that we run into, the calculations are going to be done for us using the computer. You're going to have to analyze the results, and so I'll get to that in the next page. All right, so there's our test statistic. I've got it written here again. Both the test statistic and the p-value for the test statistic are going to be found on the printout. And as we've seen before, we don't do a whole lot with the test statistics. We interpret p-values. And so how do we do that? Well, if p is low, we're going to reject the null hypothesis. And we're going to say in that case, we don't believe the null. We don't believe the values that the proportions are specified to be. So in other words, there is sufficient evidence to indicate that proportions are different than specified. We're going to need to go and find the differences, much like we did with our analysis of variance work when we compared the means. We wanted to go and detect the differences. Now, the way that we go about detecting the differences, there's a couple different ways of doing it. Because there's a couple different ways of specifying a null hypothesis, we're going to have a couple of follow-up possibilities. And I'll talk more about them as we look at the examples. I'll kind of reason through why we have a couple different ways of doing that. So that's the reject H0, and then we always have the fail to reject H0. If P is high, we're going to fail to reject H0. There's going to be insufficient evidence to indicate that the proportions are different than specified. We can't detect differences. We can't contradict the null hypothesis. We're done at that point. When we reject, there's more follow-up work to do because we want to figure out, we say differences exist, now we need to go and find them. When we fail to reject, we can't find those differences, and so we stop. Now, I know from a student's perspective, you see the word stop here, and you're thinking, oh, that's what I want to do. But in reality, we're not actually gaining any knowledge there. So the conclusion we want to make is the reject H0 conclusion, and that's what we're hoping we can say. All right, a couple other things before we go ahead and take a look at an analysis or an example. What are the assumptions? Well, there's actually 4 different assumptions that we have, and you may recognize these. Probably don't, but you might. We have n-identical trials. There are k outcomes possible for each trial, so there's k different things that can occur. The probabilities are P1, P2, P3, all the way up through PK, and the trials are independent. Let me give you an example of something that may be easy to think through. Let's say that you decide to go to a casino, and you want to play a game of chance. Well, one of the games of chance there is called craps. It's a dice game. And maybe you're concerned that perhaps the casino you're at isn't really reputable, and you're not sure that the dice are what we call fair. In other words, they're randomly giving you outcomes. And so if you think about it, when you look at any one die, now craps is played with a pair of dice, but let's look at one at a time, it'll be easier. If you think of a 6-sided die, there are 6 outcomes that are possible. There's 1, 2, 3, 4, 5, and 6. And if you were the casino and they want to claim, oh, we're honest, we're fair, they would say that the probabilities are 1/6 for each of those outcomes. Each outcome has an equal chance of being selected. And that when they roll the dice or the die the first time and it comes up a 1, that really doesn't affect the next one. So we'd say that the trials are independent as well. And so we would set up a test hypothesis where the probabilities are 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, and then we would do trials. We would sample the dice. We'd roll the die and see. If we rolled the dice, and I'll just make the numbers easy here, if I rolled the dice 600 times, and you're expecting a sixth of them to be a 1, and a sixth of them to be a 2, and a 3, and a 4, and a 5, and a 6, if you rolled the die 600 times, you'd expect to see 100 of each, right? And so what we're going to be looking at is how far do we deviate from that? Because in a sample of 600 rolls, I really don't expect to see 100 6 times, like for each of the 6 outcomes. That would be surprising if I saw it right on the money, but I'd expect to get close if the dice are fair. I wouldn't expect to see all, say, 6s and no other outcomes. That would be crazy. I don't expect to see just 1s and 6s. I'd expect to see something close to what we expected. Well, the assumptions here are we're going to do something n times. We'd roll the dice 600 times. There are k outcomes in my little example. There's 6 of them. The probabilities are 1/6 across the board, and the outcomes, the trials, are independent, meaning the outcome on the first roll doesn't affect the second roll or any subsequent rolls. These assumptions, like I said, you've seen before. We talked about these when k was 2. We talked about these being the binomial assumptions. Now I'm going to refer to them as the multinomial assumptions. Okay, not really need to know that term, but that's what they are. And then the other piece on this page of notes is the sample size requirements. This isn't the number that's observed, it's the expected number that's observed. So the expected cell counts are all at least 5. That's the sample size. And the expected cell counts are n times the individual probabilities. Now we have k levels, so there's going to be k different proportions that are specified. Really what you have to do is take a look at the smallest one. So if you look at a whole bunch of proportions and the smallest one is 0.05, you got to make sure when you multiply n times 0.05, you get 5. And so we need a sample of at least 100. If your smallest proportion is 0.025, then you need a sample of at least 200. So you really only have to check the smallest proportion in the sample size criteria. But we have some assumptions that are necessary. It's the way we take our sample or collect our data. And then we have a sample size requirement. And then we're good to go. So let's take a look at a couple examples. First example I want to look at, and the 2 examples I'm going to look at are the 2 different ways we can set up this analysis. It's the second example that you're going to be more familiar with because of what we've done with the analysis of variance work. But you can actually work this a couple different ways. So the first one, a nationwide survey of 2,119 adults. Boy, that sure seems like a large sample. But remember, when we say that, we're kind of comparing it to the value 30. You can't really do that because 30 doesn't mean anything in this problem. Answered the question, when you think of rising costs of healthcare, who do you think is most responsible? And they give you several different responses. 50% adults blame, here's the theory, 50% of adults blame insurance companies, 10% blame pharmaceutical companies, 10% blame government, 10% blame hospitals, 10% blame physicians, 5% blame some other entity, and 5% just are not sure. Now we're going to conduct a one-way test to determine if these proportions are accurate. And so if I look at these proportions here, let me underline them. 50%, that's a 0.5. There's a 0.1. There's a 0.1. There's a 0.1. There's a 0.1. So 6, 7, that's 0.9 now. There's another 0.05, so that's 0.95. There you go. The proportions sum to 1. Okay, so someone is saying here are the 1, 2, 3, 4, 5, 6, 7 categories, and we're specifying the proportions. So you got to blame something. I mean, we have an unsure category here, but you got to pick the category that you fall into. There are k outcomes. And now what we're going to do is we're going to go and sample a bunch of people, 2,119 adults, and we're going to say which one do you fall into. Now, if I take my smallest proportion of 5% here, when I take 2,119 times 5%, what is it? Well, if I multiply by 10%, it's like 211.9. So times 5% is going to be 105.95 or something crazy like that. It's a lot bigger than 5. All the expected counts are going to be at least 5. I have a large enough sample. And so here's what we found in our sample. We found that 869 blamed insurance companies. We were expecting 50%. What's 50% of that? 1,000 and almost 60. We saw a lot less than that. We're expecting 212 or so to blame pharmaceutical companies. We see a lot more than that. Another 212, another 212, another 212, 106-ish here and 106-ish there. We can see the numbers aren't all that close. And so just purely by looking at what I expect, multiplying the n, the 2,119 times the corresponding probabilities, I'm seeing that these numbers aren't all that close, but let's make it a little bit more formal than that. Let's see how the test is conducted. So I want you to be able to specify the null and the alternative. What was hypothesized? Put that in the null hypothesis. Those numbers, that's the null. The 7 cell probabilities are, there it is. And the alternative says, nuh-uh. No, I don't believe that. At least 2 cell probabilities are different than what they're specified to be. And so that's the null and the alternative that we're going to be working with. Here's the proportions. That's what the null says. And the alternative says, nope, I don't believe those values. And so that's the null and the alternative. The test statistic, well, here comes the math. There's the formula. And want any part of that? No, I didn't think so. So we need a printout. And fortunately for you, look at that, I have one for you. Now, this printout's got a bunch of stuff on it. Okay, this is the printout I got from my statistics software. And if you look at it right here, this column is the hypothesized proportion. So I put in, here are the values that we are expecting. Here are the proportions that we're expecting. And then here are the observed values. Those are the 2 columns, and I'm not hitting them all. Let's see if I think I got them there. I messed up my dots there a little bit, but those are the 2 columns that I had to put into the data set. I said, this is what we're expecting, and this is what we observed. And then statistics took my observed, counted up and said, oh, there's 2,119, and then multiplied by the expected here, the hypothesized proportion, to give me the expected. So this is just 2,119 times 0.5. This is 2,119 times 0.10, and you can see all the way down. And it's saying that's what we expect, that's what we observed. Okay, and it's taking a look at the formula. What's it do? It takes a look at the number we observed minus what's expected, that quantity squared. It's just a formula. Bottom line is, here's your test statistic. I got it bolded in red down here. That's the test statistic. It's from a distribution called a chi-squared distribution. And if we were doing rejection regions, that'd be really important for you to know about. We'd have to take a look at it. It's a skewed right distribution, and it's got degrees of freedom, and we'd have to get all up in the tables. Or the way that we're approaching things this semester, we're looking at a p-value. Look at that p-value right there. A lot of you guys saw p-values like this earlier in the semester, and you said, is that possible? And the answer is the p-value is not 0. No. The p-value is something like 0.000000002. It's really, really small. But the bottom line is, this p-value is low. This p-value is really, really low. And what do we do when the p-value is low? Well, first we're going to write the test statistic and the p-value. And then what are we going to do? We're going to reject the hoe. At alpha equal 0.01, H naught is rejected. There is sufficient evidence to say the null hypothesis is bunk. Bunk, an old school term for we don't believe it. There's sufficient evidence to indicate at least 2 proportions differ from the values that are specified. Okay, and that's this last part I have here, this find them. We're saying proportions are different than what they claim to be. Go and find them. The test of hypothesis stops with the reject H naught, and then we need to do more work. Now, earlier in the semester when we did the analysis of variance, okay, you looked and you saw that when we said means differ, we're going to go and do some confidence intervals. Same thing here. We're going to do some confidence intervals. And we actually referred to it as the multiple comparison procedure. It was called the Bonferroni multiple comparisons. And we talked in detail about that technique when we were comparing means. But remember, when we were comparing means, we had a null hypothesis that said all the means are equal. And so if we reject H naught, we're going to say at least 2 means differ, and we would want to go find which ones. This is a little different. This isn't saying all the proportions are the same. We never made that claim. The null hypothesis says P1's 0.5, and P2, 3, 4, and 5 are 0.1, and P6 and P7 are 0.05. We never claimed that the proportions are all the same, so we don't really want to go and look for differences in the proportions. We don't want to do, listen to the terminology here, we don't want to do multiple comparisons. What we want to do is multiple confidence intervals. I want to do a confidence interval for P1 to see if I believe if it's equal to 0.5. I want to do a confidence interval for P2 to see if it's 0.1 and P3 and P4. I want to create 7 different confidence intervals and find out what those confidence intervals will say about the 7 different proportions. That's how we're going to take a look at the follow-up work. We're going to do multiple confidence intervals. Now, there's a Bonferroni component, and earlier in the semester, I probably threw at you the term. What did Bonferroni say? Bonferroni says, duh. And again, duh is an old school term that means, well, think about it. If you have 7 different confidence intervals that you're going to construct, and I'll make the math easy here, if you were going to do 90% confidence intervals, what's your alpha? What's your error? If you're going to do a 90% confidence interval, what's your error? Well, your error would be 0.1, 10%. That's your error on each confidence interval. So if you have 7 different confidence intervals, each with a 10% error, across all 7 of them, your overall error could be as high as 70%. And now I mentioned to you in class earlier when we had this lecture that the errors don't add straight up like that. But it's a decent way of thinking about it. The point is your errors are going to add up over multiple intervals. And so Bonferroni says, well, don't do each one at 0.10. Split the error up. Let's say you want an overall error of 0.07 and you have 7 intervals. What should you do each one at? Well, if you have 7 intervals and you want your total error to be 0.07, do each one at 0.07 divided by 0.01. If you do each of the 7 intervals at 0.01, when you add up those 7 0.01s, you get a 0.07. Your overall reliability is 93%. Yeah, we can live with that. And so that's the multiple confidence interval idea. Now let me show you what I did on the next slide for you. I went ahead and did exactly that. I went ahead and looked back at when we were just working with a single proportion, not too long ago, right? A couple videos back, we were looking at working with a single proportion and we had a confidence interval. We plugged the numbers into the statistics software and it gave us the endpoints. Well, this time around I did the same thing, except I said, you know what? I want my overall error, my experiment-wise error, to be 0.07. So I used a 0.01 on this interval and a 0.01 on this interval and all the way down. And here are my Bonferroni multiple confidence intervals. I'm not really interested in comparing the proportion between 2 groups. That's not of interest to me in this problem. What's of interest to me is somebody hypothesized that the proportion is 0.5, and I have this confidence interval right here. So just like we've done many, many times before, let me ask you a question. If this is your confidence interval, if I ask the question, is P equal 0.5, what would you say? I'm going to say I'm 97% or 93%, excuse me, our overall error is 0.07. I'm 93% confident P1 is, what am I going to say? Less than 0.5. Why? Because every single value in that interval is less than 0.5. How about the second interval? For the pharmaceutical companies, it was hypothesized to be 0.1. What's this interval say? I believe this proportion is bigger than 0.1. I believe the next proportion is bigger than 0.1. How about this one? It says it's 0.1. I think that's too high. I think this proportion is really smaller than 0.1. Look at your endpoints. Look at this interval here, 0.047 to 0.073. Is P equal to 0.1? Nope, it's less than. We're 93% confident P is less than 0.1. How about this one, 0.1? I think it's less than. If I can draw an arrow here. How about this one, 0.05? Look at this interval here. Let me bracket this one. Is P equal to 0.05? Maybe. I don't have a problem with this one. That's the only one so far I don't have a problem with. Let's look at the last one. Is P equal to 0.05? No, I think that's higher. So 6 of the 7 proportions I have an issue with. My follow-up, my test hypothesis, my test statistic, my p-value, my conclusion is at least 2 proportions differ. My follow-up work says there's a whole lot of differences. The only proportion we can't dispute is the one in the other category. All others fall outside the interval endpoints. The test hypothesis tests to see if we believe those proportions or not. If we can reject that, the follow-up work finds where the differences are. It's called multiple confidence intervals. If you have proportions in the null hypothesis that are specified to be different numbers, that's how you approach it. Okay, that's new. We haven't seen that before. We haven't seen the multiple confidence intervals. We've seen something similar to it, and really what we've seen similar to it, I'm going to show you in this example. Let's say that the packaging of a product, here's a theory. If you're into marketing or advertising, you better agree with this theory, by the way. The packaging of a product influences sales. Yeah, it's called advertising, sure, marketing. To test this theory, we designed 4 potential packaging designs for a new cologne. So we have this new cologne, and we're going to ask 200 randomly selected men which cologne they prefer after trying all 4. Now, unknown to these men, it's the same cologne. They're going to be trying 4 different, what they think are 4 different colognes, but it's the same exact cologne, just packaged differently. And so here's what I did. I tried to come up with, here's your online world for you, folks. I did so much better when I had students give me suggestions in class, but here's what I came up with. The first type of cologne, 007. Let's say it's based on like a spy thriller type of theme and intrigue. 007 cologne, that'd be the first one I came up with. Rays. Yeah, it's pretty pathetic, I know. Like the Tampa Bay Rays, that's horrible. How about Tiger? Now, back in the day, this is an old design because back in the day, Tiger Woods was a huge, awesome golfer. And if there was a Tiger cologne, oh my goodness, it would have sold millions and millions of bottles. How about this one? Stats. A Stats cologne. Now, you're probably thinking to yourself, that's a cologne that I would never want to get. Oh, but wait, we're only in Module 3. Keep after it. You never know. By the end of the semester, I might sell you some Stats cologne. Anyway, those are 4 different styles. Let's say, and then I have a total out here for all of them. Let's say we went to 200 people and we asked them, there's 4 colognes standing on a table, and we say, try all 4. Which one? Tell us which one you prefer. Here's the results. 78 said 007, 36 said Rays, 32 said Tiger, and look at that. Stats had a respectable 54. Might be nice to tell you now that I have completely made up this data, but I'm trying to make some points here. Okay, here's what I want you to be able to think through. We want to test to determine if the proportions of selected 4 packaging designs differ. Because if the numbers are the same, it would seem to indicate that the packaging of a product doesn't matter. If the numbers are different, well, it's the same cologne, so it would have to be due to the packaging. So here's what I want you to do. What's the null and the alternative we want to test? I expect you to be able to come up with the null and the alternative. I want you to specify the proportions. If the product isn't influenced, if the packaging of the product doesn't influence sales, let me say it that way. If the packaging doesn't matter, shouldn't we get the same number, the same proportion in each? And so here's what I'm going to hypothesize. The 4 cell probabilities, P1, which would be P007, the proportion that choose 007 should be a quarter. The proportion that choose Ray should be a quarter. Tiger, Stats, they should all be the same. It shouldn't matter. If the packaging doesn't matter, that's what the null is going to say. It's going to say the packaging doesn't matter. What's the alternative going to say? Oh, it does. The way we market, the way we advertise definitely matters. And so in other words, the probabilities will change as the packaging changes. So we're going to say at least 2 of the cell probabilities differ. Now let's go ahead and get a printout. There it is. Okay, so you can see here again, I put into the computer the 25% for each of the 4 cells, or 4, I guess, packaging design, say it that way. I put in the observed that we actually saw, and then when you have the proportions that are all the same, the expected counts are all the same. We took 200 people, well, a quarter are expected in each of the 4 categories, so 50, 50, 50, 50 across the board. I saw 78, 36, 32, 54. My test statistics 26.4. My p-value again is really small. And so how do we set it up? Well, we say the same thing. At alpha equal 0.01, we reject. There's sufficient evidence to indicate at least 2 proportions are different. And I can say it a couple different ways. I could say at least 2 proportions are different than the one specified, but because they're specified to be equal, we can say at least 2 proportions are different from one another. And again, I'm going to say the same thing. We're rejecting. We're saying that proportions differ. Find them. I want you to do some more work. And so now this is very similar because, again, when we did the analysis of variance work earlier, we have mu1 and mu2 and mu3, and they were all equal. This is the same thing. All the proportions are equal. Now we're going to do a very similar technique. We're going to do the Bonferroni multiple comparisons. Now, hopefully you remember taking a look at the printouts from the analysis of variance work. Remember the homogenized groups? Okay, the grouping variable I guess that's the way it was said. It was called the grouping variable. We had columns and A's and B's and C's. Similar means were grouped together. If a letter or a column captured a couple means, that meant they did not significantly differ. And in your notes you have somewhere, means that are connected do not significantly differ. Well, now I'm going to say the same thing. Proportions that are connected do not significantly differ. Proportions that are connected do not significantly differ. Now, the downside is the software that I'm using, the statistics software, doesn't allow us to dig a little deeper and find these results. It doesn't allow us to do the Bonferroni multiple comparisons on the computer, at least not in statistics, and so I had to generate them on my own. And so here's what I got for you. I'll give you the results this way. Okay, now when you look at this, this looks completely different than what we've seen before, but here's what we have. We have the individual categories, in this case the packaging designs. We have the corresponding probabilities that we observed. Okay, we saw 32 out of the 200, that's 0.16. We saw 36, we saw 54, we saw 78. That's where these sample percentages are. So maybe this is the p hats. Let's do it that way. And then we're using these sample proportions to estimate population proportions. So when you see this part of the line right here, what that's doing, it's grouping tiger and rays together. In other words, we can't, this small difference in the sample proportions that we see here doesn't indicate that we can say the population proportion that's going to choose tiger and the rays differ. These means, or and I shouldn't say means, these proportions do not significantly differ. These don't differ. These don't differ. Proportions that are connected do not significantly differ. And you can see that. That's what the next thing I'm going to show you here. And so now you got to take a look at it. Which proportions are not connected? Well, this one isn't connected to these two. Everything else is connected. There's 4 proportions here. So let's see, there's 1, 2, 3, 4, 5. There's 6 different comparisons. I can compare tiger to rays, tiger to stats, tiger to 007. Rays to stats, rays to 007, stats to 007. There's 6 different comparisons that I make. The only ones that aren't connected are 007 and rays. There's no line that connects them, and 007 and tiger. And so the conclusion we're going to make from this is that the proportion that like the 007 packaging design exceeds the proportion that like rays, the proportion that like tiger. It's a different way of presenting the Bonferroni results. Now, the only time it makes sense to kind of connect lines and work with proportions this way is if the null hypothesis says the proportions are equal. And so that's really your first step. When you reject H0, you got to take a look at how were the proportions, how were they specified in the null hypothesis? Were they specified to be all the same, or were they specified to be different values? I'm going to refer to this technique as a multiple comparison. We're comparing proportions to see if they're the same or not. The last example, the first example I did here, where we had the proportions of 50% and 10 and 10 and 10 and 10 and 5 and 5, that was our follow-up work were multiple confidence intervals. Hopefully that makes sense. A lot of times students struggle with that idea. Make sure you get that, because I'm going to give you some problems and you're going to have to figure out which one you're working with. Most of you guys can interpret p-values really, really easily for me. When p is low, reject the null hypothesis. Piece of cake. Knowing what that means, knowing how you're going to say that, and then knowing the follow-up work now is real important. And so I want you to take a look. Take a look at some of the homework problems. And you guys know how to contact me. If you have questions, reach out. Good luck.